secure operation of a network also requires addressing implementation security. And even if the link is perfectly stabilized, there can be hardware imperfections that can introduce vulnerabilities and that would make the link susceptible to side channel attacks. For example, it could be differences in detector efficiencies or slight timing offsets in basis measurements that could be exploited by an eavesdropper. And for this, calibration routines and corrective measures are needed in order to mitigate these risks. So, in addition to this, hardware protection layers such as uh, spectral filters or power fuses, these can help prevent strong light pulses that could be injected by the eavesdropper from damaging sensitive detectors or influencing the measurements. And these precautions do form an essential part of implementation security, ensuring that the system that is deployed is in fact resilient against both accidental errors that could occur and intentional side channel attacks. With that, another important aspect, finally, we come to physical packaging of the end nodes. And here, quantum systems, they often include delicate optics, sources, and even cryogenic detectors, all of which must remain stable under operational conditions. So, while designing these end nodes, it is important to consider the swap-C constraint, size, weight, power, cost, uh, and especially for system that is intended for integration into rack-mounted solutions, or say the environment in which it is deployed would have huge thermal fluctuations or vibrations. All of these specific considerations of the application in which the end nodes would be deployed needs to be considered as well. And proper packaging will allow for long-term network operation that is reliable and can run with all the stabilization and compensation routines also in place.